Hello and welcome to another video of Cornerstones of Math. This is the second video of my recent mini-series on probability distribution, so if you haven't watched my previous video, please check the link in the description or on the top right corner. In my last video, I have dealt with discrete probability distribution. Here I present you continuous probability distribution, and while solving the problem, I will do a bunch of integrals. That sounds pretty fun, so let us dive into the problem. So the problem says, a random variable capital X can have an arbitrary value such that capital X is greater than or equal to 0 and less than or equal to 1. So our variable can have values from 0 to 1. And it has a continuous probability density function, fx, defined on the same interval. And here comes the important condition. Suppose that the probability of our variable capital X having values greater than or equal to 0 and less than or equal to small x is given as k small x cubed, where this k is constant. Then problem A, find the value of this constant k in the probability density function fx, which is pretty natural thing to ask because we have to find the exact probability density function in order to solve the following problem B, find the expected value and the variance of our random variable capital X. And problem C says find the expected value and the variance of the variable 4x plus 3. And the problem D says find the expected value and the variance of e to the power of x. Alright, let's solve this. First, the value of this constant k and the probability density function fx. You see, in continuous probability distribution, the random variable, which we often denote with capital letter X, can now have infinitely many values. Therefore, the probability of random variable capital X having a single value such as small x, is just 0. Therefore, in continuous probability distribution, we use the probability of capital X having certain range of values, for example, between A and B. This probability can be calculated by integrating the probability density function fx from A to B. This makes sense because you can think of integral as adding up infinitely many values of the function, and you can understand why the value of the function fx is not probability, but rather probability density. Anyway, first we have to find the value of k, and that is easy. We were given the probability of capital X having a value of this range from 0 to small x. And it is given that capital X can have values from 0 to 1. Therefore, we use this given condition and use the fact that if small x is 1, the probability must become 1. Therefore, using this, we have k times 1 cubed equals 1. So therefore, k equals 1. Then this condition becomes probability of capital X having value greater than or equal to 0 and less than or equal to small x becomes simply x cubed. Next, we have to find the probability density function fx. Here, let's recall the method of calculating the probability from the probability density function, by integrating. Therefore, this probability can be also expressed as integral probability density function fx from 0 to x. If using x both here and here confuses you, you can just use t here. So what we have here is integral from 0 to small x ft dt x cubed. Here we can obtain fx by simply differentiating both sides because of this mighty first fundamental theorem of calculus. So by differentiating, the left-hand side simply becomes fx, and on the right-hand side we have 3x squared. And of course the domain is from 0 to 1. And this is the probability density function. So that was the first problem. And now let's move on to the actual statistics part. The expected value and the variance of our random variable capital X. In continuous probability distribution, the expected value and the variance can be calculated like this. The expected value Ex can be calculated by multiplying the value small x of the variable to the probability density function fx and integrate it over the entire interval of the given probability distribution, which in our case is from 0 to 1. For the variance, we multiply the deviation of the value small x from the expected value squared with the probability density function and integrate it. But instead using this, it is more convenient to use this famous property of the variance, that it is the integral of x squared fx minus the expected value squared. That is, the mean of the square minus the mean squared. So we're gonna use this. In our problem, we have the probability density function fx given as 3x squared with domain from 0 to 1. Therefore, the expected value is integral from 0 to 1 x times the probability density function 3x squared dx. So integral 3x cubed dx. So 3/4 x to the power of 4. So we have 3 over 4. And for the variance, let's use this mean of the square minus mean squared property. So we have integral x squared times probability density function 3x squared dx minus expected value squared. So we have integral 3x to the power of 4 minus 9 over 16. So we have 3 over 5x to the power of 5 minus 9 over 16. So we have 3 over 5 minus 9 over 16, which is 3 over 80. And this is the variance of x. Next, the expected value and the variance of 4x plus 3. Here we will use the following useful properties of the expected value and the variance of ax plus b, where a and b are constants. For the expected value of ax plus b, we simply multiply ax plus b to the probability density function fx and integrate them. Then we have a integral x fx dx plus b integral fx dx. Here, this is the integral of the probability density function over the entire domain. So this is simply 1, which is equivalent to the sum of all probabilities. And this part, the integral of x fx, is just the expected value of variable capital X. So we have a times expected value of x plus b. So we obtained this property. And for the variance of ax plus b, let's use the mean of square minus mean squared formula again. So we have mean, the expected value of ax plus b squared minus the expected value of ax plus b, and this entire thing squared. Here the first term is integral of ax plus b squared fx, and we have already obtained the expected value of ax plus b, which is this. So we have a expected value of x plus b squared. So we have integral a squared x squared plus 2abx plus b squared fx dx minus a squared ex squared plus 2ab ex plus b squared. Therefore, we have a squared integral x squared fx dx plus 2ab integral x fx dx plus b squared integral fx dx minus a squared ex squared minus 2ab ex minus b squared. Here, this term and this term gives a squared integral of x squared fx dx minus ex squared, and this is just ex, so we have 2ab ex, and this is 1, so we have b squared, and we have remaining terms minus 2ab ex minus b squared. Here, this part is mean of squared minus mean squared, so this part is simply the variance of x, and these two terms cancel out, and these two terms cancel out, so we have a squared times variance of x. So we have obtained these properties, and using this we can easily calculate the expected value and the variance of 4x plus 3. So using these previous results, the expected value of 4x plus 3 is given as 4 expected value of x plus 3. Therefore 4 times 3 over 4 plus 3. So we have 6. And the variance of 4x plus 3 is 4 squared times variance of x. So 16 times 3 over 80. So 3 over 5. So this was the third problem. And finally, the expected value and the variance of e to the x. Here we cannot use the linear relationship we used in the previous problem. So here we calculate the expected value and the variance from the very definition of the expected value and the variance themselves. First, the expected value of e to the x can be calculated by integrating the function e to the x times probability density function fx dx. Therefore, with this probability density function, we have integral 3x squared e to the x dx. This integral can be calculated using integration by parts twice. So here, we let x squared as u and e to the x as v prime. Then, u prime is 2x and v is e to the x. Therefore, we have first 3 times uv, so x squared e to the x, 0 and 1, minus integral 3 times u prime v, so 6x times e to the x dx. Now the first term gives 3e, and for the second term, we use the integration by parts again, now letting u as x and v prime as e to the x. Then u prime is 1 and v is e to the x. So we have 6 times uv, so x e to the x, minus integral 6 u prime v, so 6 e to the x dx. So we have 3e minus 6e minus the integral of this is 6e to the x. So in the end we have 3e minus 6. So this is the expected value. Similarly, for the variance, we use the mean of square minus mean squared. So we have integral e to the x squared fx dx minus expected value of e to the x squared. So we have integral 3x squared e to the 2x dx minus the expected value of e to the x is this. So 3e minus 6 squared. For this integral, we use the integration by parts. So u equals x squared and v prime equals e to the 2x. So we have u prime equals 2x and v equals 1/2 e to the 2x. So we have 3uv, so 3 over 2 x squared e to the 2x with 0 and 1 minus integral 3u prime v, so 3x e to the 2x dx minus this term. So we have 3 over 2 e squared minus, and here we use the integration by parts again. So u is now x and v prime is e to the 2x. Then u prime is 1 and v is 1/2 e to the 2x. So we have 3uv, so 3 over 2 x e to the power of 2x minus integral 3u prime v, so 3 over 2 e to the 2x dx minus this, so 3 over 2 e squared minus 3 over 2 e squared minus the integral of this is 3 over 4 e to the 2x. So we have this minus 3e minus 6 squared. So these two terms cancel out and we have this term. So 3 over 4 e squared minus 1 minus this part expanded. So 9e squared minus 36e plus 36, which gives minus 33 over 4e squared plus 36e minus 147 over 4. And this is the variance of e to the x. And that was all for today's video. If this video was helpful, please give a like and also subscribe to my channel. And in case you haven't seen my previous probability distribution video, please click the link on the screen. Thank you for watching, and I will see you in another video.